All right, so today we're going to talk about DeMorgans equivalences, or what the book calls DeMorgans laws, and that's all we'll talk about in this lecture. These are really powerful equivalences, and they also take just a little bit of getting used to. So the DeMorgans equivalences are the only ones that are eponymous. They're named after a person, a guy named Augustus DeMorgan, who was a very important logician. And the equivalence has two forms, and you're familiar with them already from our refutation tree rules. So the first form says that it's not the case that A and B is logically equivalent to not A or not B. And the second form tells us that it's not the case that A or B is logically equivalent to not A and not B. So our previous familiarity with these stems from thinking of the equivalence in this direction, right? So if you think of the first one, what we would do is we would take it's not the case that A and B, and we would apply the negation, the negation conjunction rule, and we would get not A or not B, right? Which is what we've got right here. And also you'll remember that we would take the negation disjunction rule, not A or B, and we would apply that to get not A and not B, which is what we've got here. The important thing to remember, though, is, well, first of all, we're not doing refutation trees. This is the propositional calculus. And the important thing to remember is that this is a biconditional, right? It goes both ways. And so we don't just think of it the way we thought of refutation tree rules. Rather, we think of it the way we think of it is that these formulas can be substituted for each other. So not only can this be substituted for this, but this can be substituted for that. Not only can this be substituted for this, but this can be substituted for that. Okay? So very important to remember that we're doing substitutions when we work with equivalences, because that really allows you to work this system and get a lot more out of it more quickly. Okay, so the DeMorgans equivalences are super powerful. In fact, there's all sorts of proofs that we wouldn't have even given you to work on until now, because we didn't have DeMorgans, and you would have essentially had to prove DeMorgans, which isn't really easy, in order to do the proofs. Now, sometimes it's not easy to see that the DeMorgans equivalence can be brought into play. For example, it doesn't initially apply to this formula at all, P or not Q. It doesn't apply because well, if you look at the rules above, say look at A or B, right? We have only one of them is negated, right? And so you might look over here, right? But this one is not negated. P is not negated, so we have a negated formula, but not a negated formula here. But the thing is that, as you know, using double negation, you could double negate that formula if you wanted to. So you could just render P or not Q into it's not the case that P or not Q by one application of double negation. And then you can see you do have an instance of this formula. So you have not Q being not B, and not A being not P, right? So, not A being not P, where A is not P, right? So if you think of A as being not P, then you have this formula. And so if you do a substitution on this formula, what you're going to get is the negation, right, on the outside, and then leaving A, which is not P, and leaving B, which is Q, and you convert that to an AND, right? So you got to think about these a little bit, and eventually it will start to become fairly intuitive for you. I'm going to give you a bunch of practice at the end of this video. Now, the other thing you have to remember, of course, is that these rules are all written in the meta language, which means that A and B can represent any formulas whatsoever, not just atomic propositions or their negations. So you take a formula like this, it's not the case that if P then Q and not R or T, you can apply DeMorgans to it if you want. You should go ahead and do it. What you end up with is it's not the case that if P then Q, or it's not the case that R or T, right? So you've just basically got this formula, not A and B, where if P then Q is A and not R or T is B, right? So not A or B over here is going to be, it's not the case that if P then Q, or not R or T. And actually, if you look at this, you can see that if you wanted to, again, you could apply DeMorgans to this formula here. The reason you can, actually, you're applying it to a sub-formula, which is, it's not the case at R or T, right? Why can you do that? Well, this not R or T corresponds to, it's not the case that A or B, right? So if you take not R or T, just think of that as being an entire formula for you to apply DeMorgans to. You just forget about this negation over here, right? And not R or T becomes not R and not T, right? So you're substituting this blue formula for this blue formula, and the negation, the outside negation, is completely unaffected. Okay? Okay, so let's do a few proofs where the DeMorgans rules really help us out a great deal. Right, so as always, you should try to do these yourself. We'll start with simple and gradually make it a little more interesting. So you've got, it's not the case that P and Q. If R, then P and R. And you're asked to show that not Q. So we stare at this a little bit and you can see that, well, you could have P if you wanted to. And now that you know DeMorgans, you know that you could have not P or not Q, right? So not P or not Q by 1 in DeMorgans, only one rule, because one line, excuse me, because this is an equivalence. And then you remember you've learned a derived rule, which is going to help you out a little bit once you get P by 2-3 conditional elimination, because P is going to apply to not P or not Q by disjunctive syllogism, but of course not until you do what? Right, you got to change it to not P by double negation, because it has to actually be the negation of not P. So you got not P now, which gives you not Q by 4-6 disjunctive syllogism. Okay, so you want to know how powerful DeMorgans is. Try doing this proof without it. Use any rules you want with except DeMorgans and try to prove it. All right, so this next one Again, you should try to do it on your own. This next one we're asked to prove. It's not the case that not T or not S follows from P and Q or not S and T, and not Q or not P. Well, what I see when I look at this for a while is I see an interesting relationship here between P and Q and not Q or not P, because this is definitely an instance of DeMorgans, right? Not Q or not P, which converts to it's not the case that Q and P, right? And the reason that's interesting is because this is basically the negated version of this. When I say basically, that doesn't mean it's the same though, right? You can't apply these yet because you first have to apply the commutation rule, which is also an equivalence. So Q and P is logically equivalent to P and Q. So you substitute P and Q for Q and P, and now you've got the negation of this first formula, P and Q, which by disjunctive syllogism gives you this formula, not S and T. Right? And why is that cool? Well, it's pretty cool because this is very, very close to this, right? Again, by a DeMorgans substitution. So you can't perform DeMorgans on this yet. Why not? Well, because it doesn't have a negation outside of parentheses. And the inside, you don't have two negated propositions. You only have one. You have a negated not S. So what can you do to fix that? Well, you can double negate the T, right? And so now, if you think of not S as A and not T as B, you've got not A and not B, right? And so not A and not B goes to not A or B, right? Again, not S being A and not T being B. So we have, it's not the case that not S or not T, and then again, by just one application of commutation, we get our conclusion. Okay, so you should definitely make sure you can do those two problems on your own before going to the next two. Just shut us down and knock those two problems out. Even if you're just sort of remembering the steps at this point, that's good. That's a useful thing to do. Okay, the next one. Here we're asked to demonstrate a conditional, which of course always is going to suggest to us that we're involved in a conditional proof. If P, then not S or R, S and not R implies if P, then Q. Now, I could just go ahead and hypothesize P here right away, but that means anything I do after that is going to be locked up behind a drop bar after I drop it. So I might just play with this a little bit first. I can see that S and not R has a very interesting relation to not S or R. What if I were to apply DeMorgans to S and not R? Well, unfortunately I can't because, right, I have a conjunction, but I would need the S to be negated. I would need, both formulas have to be negated. Now, you don't want to negate the S, of course, because that's not what it says. But as before, you could change this into not S. And so now you have not S being A and not R being B, right? And so what you get as a result of the application of DeMorgans to this is going to be not the case on the outside now that not S or R, right? Because both not S and not R, right, lose their negations, but this one stays, right? Because this negation here doesn't go away, right? So essentially you can think of it as you're pulling one of the negations out, right? So you pull this one out, you pull this one out, this one stays behind, You put the negation on the outside, and the disjunction, the conjunction, becomes a disjunction. All right, so we actually do now have exactly the negation of this formula, right? And that's cool because we know of a rule called modus tollens that allows us to generate not P. Well, we don't want not P. We want if P then Q. But now it looks like we can get what we want, right? Especially if you remember our contradiction rule. So what you're going to do is go ahead and hypothesize P now. What you want is Q, but 5 and 6 contradict each other, right? Not P and P, and the contradiction rule says, well, anytime you have a contradiction, you can just write anything you want, right? So you got not P and you got P, and that allows you to write Q. Now remember, we were not doing a negation introduction here. We were just applying this new rule, derived rule, the contradiction rule, and so we're not doing any kind of we don't have to write the conjunction. We're not involved in a separate hypothetical rule. We're just using the conditional introduction rule. Okay, so we've got Q, and that allows us to write if P then Q, right? And that's all there is to it. Just as a little aside here, to take a breath for a second, some of you still might be weirded out by the contradiction rule, right? The contradiction rule, con, right, is weird. Remember, to get rid of some of the weirdness, let's do a little exercise, right? Now, I've told you several times that the fact of the matter is that in logic, a contradiction will implies anything at all, and that's what we're taking advantage of. How can we prove that to ourselves really, really quickly? Suppose we have P on line 1 and not P on line 2, right? That is a contradiction. Now, let's prove anything we want not using the contradiction rule. On line 3, I'm going to write P or anything I want, okay? So whatever I want. So what I want is T. I've just pulled that out of the air, okay? By or introduction, right? Or introduction on 1. Okay, but now I know not P. I know not P. Because I have P or T and not P, I have T, right? By 2, 3 disjunctive syllogism. Okay, we couldn't show it this way before because we didn't have this rule. But now that we have the rule of disjunctive syllogism, which I think probably makes total sense to you, you have to see that the contradiction rule makes sense, because all you need is disjunctive syllogism and or introduction. We could get rid of the contradiction rule and just make you do this every time. But why? There's no reason to. So that's why we have the contradiction rule. Oop, forgot to drop the bar. All right. Okay, so we just have one more, and then we'll give you a bunch of little review exercises just for identifying DeMorgans. Let's do this one. So here we have this massive disjunction, K or M or K or R, which is supposed to imply this conditional, if not K, then M or R. Go ahead and give this a whirl. In the old days, we would have said, okay, look, this is a disjunction, so we're probably going to be doing a disjunction elimination. And by the way, these two are disjunctions too. So, right, so we'll probably be doing a disjunction elimination and then another one inside that. We'll basically be in disjunction elimination hell. So let's see if we can avoid that. We see that we are going to prove a conditional, and so a nice way of simplifying your task always is just to hypothesize the antecedent, not k, and then our task, of course, becomes to derive m or r. Now, not k doesn't give us m or r here. And so what you should start exploring is like, okay, does not k, could it give us, say, with disjunction introduction or something, could we somehow involve ourselves in this disjunctive syllogism? That would be an intelligent way to proceed. But no, look, I mean, you could like go, okay, look, how about not k or not m? Well, yeah, that's good, and that would actually take you to not k and m by DeMorgans, but you don't want not k and m. You would like not k or m, right? So that that's not productive. Let's go ahead and erase that. You got to go through this, though. I mean, you got to play, experiment, use your little eraser. So you're stuck, really. And so what do you do? Well, anytime you're stuck, what do? What you do is you do a negation introduction, right? So go ahead and hypothesize the negation of m or r. Now, what does that do for you? Well, that sort of like gives you something to play with. Right now you got, it's not the case that m or r, and by DeMorgans that goes to not m and not r. And that's kind of like, that's great, because anytime you create a conjunction, you've created a lot of information. You now have free and clear not m and not r. Well, now what could you do? What could you do with not m and not r? Right? You've got not m, you've got not r, and you've got not k, remember, right? So what if you put not k and not m together, or alternatively not k and not r together? If you apply DeMorgans to that, you're going to get a negated disjunction, right? So say take not r by hand elimination on 4 and put it together with not k, and you got not k and not r. So go ahead, you see what's happening? So go ahead and see if you can take it on in from here. All right, so that's going to become, it's not the case that k or r, which gives us k or m by 1/7 disjunctive syllogism. So we have k or m. But we also have not k, right? K or m and not k, what does that give us? That gives us m. And what do we want? Well, we want m or r, but we have m, so we have m or r, right? Now you might get kind of confused here, right? Because we have m or r, so it looks like, hey, we can write if not k, then m. Oh, wait a minute, we were doing a, hey, hold it, we were trying to get a contradiction. We weren't trying here to derive m or r. We were trying to get a contradiction. Crap. But then wait. I have a contradiction. M or r, not m or r. Right? So this is just funny where the contradiction is a formula that you're trying to get. So you write m or r and not m or r by 10-3 and introduction, which gives you not m or r, right? The negation of the original hypothesis. So not m or r, and now you can drop a line, and now you know that if not K, then not M or R, but you don't want that. You want not if not K, then M or R, but you can have that through 12 in double negation, right? And now you're ready to state your conditional and drop your line. All right? That's kind of a cool one. Again, make sure you can do that before going on. And now we'll just go ahead and finish up with some review questions on just doing the DeMorgans operations, okay?